Hi, I'm Miss Hall, and this is Lesson 1.4, the Real Number System. The aim of this lesson is to figure out how we can classify numbers in the real number system. Well, let's begin with what's a real number? A real number is any number that can be placed on the number line. We use the symbol, this fancy R, to denote the set of all real numbers. Since there are so many real numbers, we classify them into smaller subsets. So here we go. Here is the set of all real numbers. And real numbers further get divided into rational numbers versus irrational numbers. I want you to look at ratio here because rational numbers are numbers that can be written as a fraction or a ratio. So some examples of rational numbers are, say, 2/5, 4/3, -8, 3/1. All of these can be written as ratios or fractions versus irrational numbers. I'm going to run out of colors, but let's go. Are numbers that cannot be written as a fraction. This means they have never-ending decimals. Never-ending decimals without a pattern. A classic example of an irrational number is pi. We also have, for example, the square root of 3. Okay, let's go back into the world of rational numbers, numbers that can be written as ratios. We can further go down into not only can be written as fractions, but there's another subset of rational numbers that are called integers. And these are numbers that have no decimal. So we have examples like -7, 31, 0. These numbers have no decimals. Getting more specific than integer, we also have whole numbers. And these are non-negative. Oh, don't repeat colors yet. Let's go here. Non-negative numbers with no decimals. So these are non-negative integers. Non-negative integers, we go 0, 1, 2, 3, 4, all the way up. And more specific than whole numbers are natural numbers. And these are the counting numbers. These are the ones you learn when you were little. These are the counting numbers. They're all whole numbers except for 0. So we have 1, 2, 3, 4, 5, and so on. Let's push up just a little bit, see if we can keep that in frame. Great. Example 1. Name all of the sets of numbers each of the following belong to. So 12/9, we'll start with the biggest. Well, it's already written as a ratio, so I know it's a rational number. Oh, even bigger than that, it is a real number. So it is a real number, and it is also a rational number. Can I get any more specific? No. It will have a decimal. If I go ahead and reduce this, I get 4/3, which is 1.3 repeated. So there is a decimal value there. Let's go down to B. Okay, this is a real number. It can be rewritten as a ratio, as a fraction. One kind of cheat that I'm looking at is never-ending decimals without a pattern. Well, this decimal ends, so it can be written as a fraction. So it is rational. It is not an integer, because then it would have no decimal, and this one does. Square root of 49. It's going to help me if I simplify that first to 7. So 7 is a real number. It is rational. It can appear as a ratio. It is an integer. It is a whole number. Let's see, integer, it is a whole number. And it is a natural number. Going on to the square root of 3. If I had my calculator, I might put that in my calculator to see what it would give me. In this case, it will give you a non-repeating number, meaning it is real. We can put this on a number line, but it is irrational. It cannot be represented as a fraction. Now we have 4.6 repeated. This is a real number. It is not a never-ending decimal without a pattern. It is a never-ending decimal, but with a pattern, which means it can be represented as a ratio. So it is a rational number. It's not an integer. There is a decimal there. Finally, we end with negative 24 over 8. That can be simplified to negative 3. And what do you know? It's a real number. Shocking. It can be written as a ratio, so it is a rational number. It is an integer. And it is not a whole number because it is negative. Example 2. Read each statement below to determine whether the statement is always true or sometimes true. The difference between a whole number and a whole number is a whole number. Okay, so whole numbers are non-negative numbers with no decimal. So let's see, I have 7 and 2 are whole numbers, for example. The difference between whole numbers is a whole number. Well, in that case, yes. So that works. But now let me flip these whole numbers, and I will get a negative, which is not a whole number. So this one is sometimes true. Next up, square roots are irrational numbers. Well, I did give the example of the square root of 3. That is an irrational number. But then we also saw from the first example, I'll pull it from the first, the square root of 49 is 7, which can be written as a ratio, so it's not an irrational number. So this breaks it. So this statement is sometimes true. Last one of example 2. The sum of an integer and an integer is an integer. Okay, well, an integer is a number with no decimals, so let's do negative 3 plus, because it's the sum. Let's do 1. When I add those, I get negative 2. Great, that's still an integer. Maybe let's try 5 and negative 6. I'll get negative 1. Can I think of a case where 2 integers would add to not an integer? No, I can't imagine a time where suddenly a decimal would get involved, for example. So this one is always true. It is time to pause the video and try these on your own. Unpause when you are ready to check your answer. For this problem, it says identify all the sets that the number belongs to. Well, I am going to reduce this. How do I want to reduce it? Let's reduce it this way, the square root of 16 over the square root of 25. And that is 4 over 5. Yes, I was trying to figure out if I could reduce this fraction, but they don't have, neither the numerator or denominator has a common factor, so there's nothing to reduce. So how I can simplify it further is by taking the square root of the numerator and denominator and getting 4/5, which is a ratio. So I don't know why I boxed that part in. This is a real number. It is a rational number. And it will be a decimal value, so I can't go further than that. So I really should box in real and rational. Determine whether the statement is always true or sometimes true. Fractions are integers. Well, let's see. We've got, for example, 4 over 1. That's a fraction. It happens to be also an integer. Let's do negative 4 over 1. That also is an integer because integers can be positive and negative, just have no decimal. But if I think of another fraction, that is no longer an integer because integers are non-decimal values, both positive and negative. So this is sometimes true.